Antikythera Mechanism, the mechanical cosmos. The sea had already chewed it to lumps when the sponge divers brought the wreck up in 1901. They tossed bronze statues and amphorae into daylight. The lump that mattered looked worthless until it split. A gear wheel flashed under museum light, teeth as fine as a watch. Stakes first. If we're right about this device, it pushes precision mechanical computing back into the 2nd century BCE, maybe earlier. Not water wheels, not mill cogs, differential gearing, predictive astronomy, eclipses, cycles, games, calendars, all encoded in bronze. If that's true, the simple ancient story dies, and so does the comforting straight line of progress. What actually happened next is a tangle of people and patience. Decades passed with the fragments mislabeled and misunderstood. The inscriptions were almost invisible. Then imaging changed everything. Microfocus X-ray CT peeled corrosion away without touching it. Gear outlines emerged. Tooth counts snapped into ratios. Researchers began to see not a curiosity, but a machine with intention. You could crank it and watch the sky move. On the front, dials for the sun and moon, and based on reconstructions, the known planets: Mercury, Venus, Mars, Jupiter, Saturn, each with its own tricky motion. The moon's non-uniform speed wasn't hand-waved. It was modeled mechanically through a pin-and-slot epicyclic train. On the back, spiraled scales for the metonic cycle, Saros eclipse cycle, predicting when the sky would darken, and even a callippic refinement. There's evidence of an Olympiad indicator. This wasn't decorative. It was a compact cosmos you could hold. Human moments anchor the story. The sponge divers surfaced sick from the depths, hauling history they didn't recognize. In the mid-20th century, Derek de Sala Price took a big swing. He argued for a complex gearwork that many doubted. Years later, Tony Freeth and his team used high-resolution scans to decode inscriptions and propose a full kinematic model. They weren't inventing romance. They were counting teeth, matching cycles, and testing whether the math drove the metal. Each tiny inscription, each slot, each shoulder on a gear had a purpose. When a modern watchmaker builds a replica and it bites, you feel the mind that designed it. Here's the impact ripple. One artifact implies a workshop. A workshop implies a culture of toolmakers, measuring systems, and teaching. You don't jump from hammering shields to cutting 1.5mm gear teeth with precise counts overnight. That means lost lathes or equivalents, jigs, and a knowledge chain, artisans who knew how to engrave scales on curved plates and align axles in tight tolerances. Once you accept the mechanism is real, you have to ask, where are the siblings? Where's the scrap? Where are the manuals? Suppression is quieter here, more bureaucratic than malicious. For decades, the device lived as an oddity, told in a paragraph under a glass case. Scholars who pushed its complexity met raised eyebrows. Access to the fragments was limited, imaging time was scarce. Without high-resolution scans, arguments devolved into hand-waving. Gatekeeping didn't look like censorship, it looked like paperwork. Meanwhile, the public conversation filled with either wild speculation or yawns. Both outcomes keep the device inert. Let's be clear on facts versus fantasy. It did not prove ancient space travel. It did not require lasers. What the evidence supports is more startling and more human. Hellenistic engineers, using careful craft, built an analog computer to predict the sky, drawing on Babylonian cycles, Greek geometry, and practical mechanics. The error bars are present. Fragmentary pieces mean some reconstructions may be refined, but the core is solid, predictive, geared astronomy. And then there's the workshop question that won't go away. Workshops make families of objects. If this was a one-off gift, it still needed a shop to birth it. If it wasn't, then somewhere in silt or in private collections, other devices wait, perhaps burned down to stains on wood, perhaps corroded to silence, perhaps miscatalogued as gear-like fragment. This is where the suppression mechanism intersects with loss. When archives burn or empires fracture, machines go first. Metal gets melted. Inscriptions get scraped. Skills die when apprentices stop showing up. But consider what nobody knew at the time. The mechanism's gear trains indirectly point to a wider gear culture. Elsewhere in ancient China, differential concepts appear in the south-pointing chariot. In Alexandria, mathematicians wrote methods we only glimpsed later through palimpsests. The idea that complex machines emerged in a vacuum feels thin. Meanwhile, comparison with later Islamic astronomical instruments, the astrolabe tradition, the Zij tables, suggests an ongoing conversation across centuries, languages, and ports. The Antikythera mechanism isn't a lone miracle, it's a survivor. On the ground, the stakes get personal. Picture a craftsman setting a pivot, knowing a slight wobble will throw the moon off by days over a cycle. That's not myth. That's muscle memory, metal filings, fingertips. When we reduce this to ancient genius as a vague label, we miss the living system. Supply chains for bronze, workshops near libraries, sailors moving ideas as fast as they moved cargo. Lose any node in that network, trade routes, a patron, a scribe, and the machine line ends. Here's the turn. If a pocket cosmos sat on a shelf in a Hellenistic city, what sat next to it? A portable astronomical calendar suggests precise surveying. Precise surveying suggests better maps. Better maps lead you to a desk where a cartographer draws a coastline ahead of his time. While that was happening in the Aegean, another tradition was recording port-to-port bearings with unnerving accuracy. If they tracked the heavens this cleanly, someone somewhere was tracking the earth with equal nerve. Baghdad Battery, power or ritual. From the sky to a clay jar in the dirt, small enough to fit in your hand, strange enough to split a room. A pot, a rolled copper cylinder, an iron rod sealed with bitumen, found near ancient Ctesiphon in the 1930s and filed as miscellaneous. Then someone asked an annoying question: what happens if you add an electrolyte? Here are the stakes. If this little assembly is a battery, a galvanic cell, then ancient craftspeople knew how to pull a current on demand. Not a grid, not streetlights, but a spark you could carry. That opens doors, electroplating metals thinly and consistently, delivering therapeutic shocks, igniting mixtures cleanly. It's not civilization changing by itself, it's workshop changing. And workshops change civilizations. The action begins with a lab director staring at corroded metal inside clay. He proposes the unthinkable: it's a cell. Copycats build replicas with lemon juice, vinegar, grape juice, even copper sulfate. The meter ticks, half a volt here, a volt there. String a few and you can plate a faint film of copper or make your fingertip tingle. On camera, the beam of skepticism wobbles. People want a show. The jar quietly delivers a number. But the jar fights back. No wires in the dig report, no plugs, no obvious terminals. The copper tube isolates the iron, the bitumen seals the assembly. If they were routinely using electricity, where are the switchable circuits, the sockets, the instruction tablets? Archaeologists push hard, electrolytes corrode, wires rot. Absence isn't proof. Still, you feel the tug, so we pivot to function. What would portable power look like in a world of artisans, not factories? Think plating. If you're a jeweler with limited gold, an electrochemical bath can make a thin layer gleam like wealth. It's faster than leafing, more uniform than rubbing. Experiments show plating from Baghdad Battery replicas is fussy but real, low current, long soak patience. In elite workshops, time is a tool, or think medicine. A mild shock is novel, memorable, ritualizable. Pain relief, demonstrations, temple miracles. None require a manual, only the effect. Meanwhile, we reconcile the counterpoints. No grid means no expectation of wires in walls. The device could be niche, portable, episodic, brought out for special tasks, then stored. Copper and iron were valuable. Assemblies would be reused until they died, leaving little debris. Electrolytes might be seasonal, vinegar from wine, lemon juice where available, brine anywhere. That leans toward a microtech mindset, targeted advantages, not universal infrastructure. Suppression here doesn't wear armor, it wears labels. For decades, the jar is called a storage vessel, a ritual container, a curiosity. Replication work happens on TV instead of journals, so scholars treat it like a circus trick. Museum access is limited, provenance papers are thin. The quickest way to keep a device inert is to keep it ambiguous. Call it ritual and the technical questions stop cold. The human angle keeps whispering. In a back room, an artisan tests acids with a reed dropper, watching for color and smell. He lowers a copper sheet into a solution, waits, lifts, rubs, frowns, tries again. He doesn't need the word battery. He needs the result, a brighter finish that sells for more. Across town, a healer taps a patient's skin with a wetted cloth and touches 2 terminals. The patient startles, then laughs. The healer smiles and calls it a demonstration of balance. What nobody knew at the time was how sticky this argument would be. The jar can produce electricity, that's shown. Whether it was intended to is the not. There's no electroplated artifact everyone agrees on from that context. Alternative explanations, scrolls storage, ritual perfume infusers, fit the silence too, so we draw the boundary honestly. The Baghdad Battery sits on the fence between plausible power and plausible ritual, with experiments nudging it toward power and archaeology tugging it back. Impact, if we allow the nudge, is subtle but real. Portable current implies mindsets willing to exploit invisible forces through repeatable setups. That dovetails with chemical craft, dyes, mordants, acids, that we know flourished. Even if this jar wasn't a battery, the fact that it can be won with period materials shows the threshold was crossed in principle. That puts electrochemistry within reach of a curious workshop long before textbooks. And here's the hinge. If some ancients held a flicker of electricity in clay, then precision didn't just live in gears. It lived in solutions measured by taste, in drop counts and patient waits. From portable power to precision you can't fake is a narrow step. Because once you can see more clearly, on metal, on stone, you start asking for tolerances that copper chisels alone won't satisfy. Portable power is one thing. The next question is sharper. Who carved stone like it was turning on a lathe? Egyptian hardstone precision, the impossible tolerances. The first time you run a finger along a pre-dynastic bowl cut from diorite, it feels wrong, too smooth, too even, like the surface forgot to be stone. Then you spot the concentric striations curling inside the lip, evenly spaced, like a machine fed the tool at a steady rate. This is where the stakes hit. If bowls, cores, and sarcophagi in granite and diorite hold tolerances we associate with lathes and precision abrasives, the copper chisels and elbow grease story is missing chapters. Not aliens' methods, not magic process control. To understand why that matters, we need to walk into the measurements, not the myths. Flinders Petrie wasn't dazzled by scale. He was bothered by regularity. He measured curvature, coaxial alignment, and interior orthogonality on pieces where a human body barely fits. He called out feed marks that spiraled with a constant pitch, the kind you see when a tool advances in a controlled, repeatable motion. Fast forward, modern researchers bring calipers, laser scans, and profilometers to recheck claims. Some heroic numbers shrink under scrutiny. Others hold up enough to force better questions. What actually happened on the ground? Granite and diorite are stubborn, hard, brittle, laced with quartz. The orthodox kit lists copper saws, copper tube drills, sand abrasives, bow-driven spindles, and plenty of water. With quartz sand as the cutting agent, copper is just the carrier. Replication experiments show you can core drill granite with a copper tube and abrasive slurry, leaving a telltale central drill core and spiral striations on both the core and the hole. Increase the bow speed or the abrasive quality, and the feed marks tighten into regular ribbons. Switch to emery or corundum if you can source it, and your removal rate climbs. Nothing modern there, just stubborn patience and materials know-how. But the tolerances still nag. Inside corners of sarcophagi approach right angles with surprising orthogonality. The lid meets the box with small, consistent gaps. Surfaces flatten across long spans better than you expect from casual rubbing. That suggests fixtures, straight edges, squares, plumb lines, and reference flats, likely diorite-on-diorite rubbing with abrasive to average out peaks, like lapping plates in a machine shop. To hit consistent parallelism, you need checkpoints. Red ochre transfer, strings under tension. Water surfaces as level references. It's not magic to an engineer, it's process discipline. Then there are the bowls and vases with deep interiors and thin, uniform walls. A hand and a scraper inside a narrow throat invite chatter and asymmetry. Yet some walls stay concentric within a few millimeters over depth. The spiral feed marks on interior surfaces read like a logbook. Advance, rotate, steady hands or steady fixtures. Was there a lathe? Not necessarily a metal bed lathe with lead screws, but a rotating workpiece held between centers or on a mandrel, driven by a bow or cord with abrasives doing the cutting. Replicators have turned soft stone on simple rigs. Hard stone just scales the patience and the abrasive. The suppression pattern here wears a different mask, compliments that shut down inquiry. Artistic genius becomes a label that floats above the technical problem instead of diving into it. Museums display the finished forms under dramatic light but rarely show the toolkits. Funding gravitates to tomb texts and iconography. The shop floor gets a paragraph. When artisanship is framed as miracle, engineering questions sound rude, so the questions stall. Let's keep the facts clean. We don't have a stash of diamond-coated drills from the early dynastic period. We don't have a copper lathe with a lead screw. We do have thousands of hard stone vessels, drill cores that match abrasive-driven tube drilling, saw marks, and abrasion signatures. We have Petrie's notes, later skepticism, and modern remeasurements that prune the extremes but leave a core truth. Some objects required controlled rotation, consistent feed, and reliable metrology. That's not beyond human hands. It's beyond casual hands. Human moments bring it back to scale. An artisan leans over a rotating stone, sprinkling slurry, listening for the pitch that signals a stable cut. A master checks a flat by mating two stones and twisting until the grit whisper evens out. An apprentice learns to read scratches as sentences. Too deep means too much abrasive, too smooth means glazing, uneven spirals mean inconsistent pressure. The shop smells like wet sand and copper. This is craft as algorithm. What nobody in that shop knew was how their precision would be read centuries later, as impossibility rather than instruction. Some modern voices jump to forbidden tech. Others respond by minimizing the precision to save the story. Neither helps. The interesting middle is a toolkit we can reconstruct. Abrasive hierarchies, rotating rigs, lapping plates, gauges, and a culture that rewarded repeatability. That implies logistics, quarries delivering consistent blocks, workshops with standardized jigs, foremen who timed tasks and rationed abrasives. Impact spreads quietly. Once you can true a surface and keep it true, you can align shafts, seat doors, build channels that flow as designed. Stone that behaves like metal hints at metallurgical competence nearby. Copper alloys tuned for stiffness in carriers, bronze wedges that survive repeated setting, binding agents that hold abrasives without glazing. The precision in stone doesn't prove advanced metals, it motivates them. And when you can measure better, you start asking for parts that meet the measure. There's an open loop we can't close yet. The math and the tools had to live somewhere, drawn, taught, inventoried. Where are the toolkits? Wood rots, fibers vanish, copper gets recycled. The evidence path rewards durable showpieces and punishes humble jigs. That's a preservation bias, not a conspiracy, but bias still hides. So we look for ghost signatures. Consistent bore diameters that fit standard mandrels, repeated spiral pitches that imply common bow stroke lengths, abrasion residues that map to regional emery sources. Meaning lands here. Calling these objects impossible flatters us and erases them. Calling them just art erases the system that made the art possible. The honest frame is harder and richer. Ancient shops ran process control without paperwork, and the stones remember. And when stone starts behaving like metal under a disciplined hand, you should expect, somewhere close, a metal tradition doing things ahead of its script. Now that we've watched stone take a polish that survives millennia, let's step to a material that learned to heal itself in the sea. Roman liquid concrete, the self-healing formula. From stones that act like metal to a building material that behaves like a living thing. Stand on a crumbling modern pier and look across the bay at a Roman harbor still shrugging off waves after 2 millennia. The stakes are simple and sharp. If their concrete not only survived seawater but grew stronger because of it, then materials science isn't a straight climb. It's a loop, and we've been relearning what they already practiced. Here's what actually happens inside that ancient mix. Roman builders hauled volcanic ash, pozzolana from the Bay of Naples, mixed it with lime, aggregates, and seawater, and poured it into wooden forms sunk in the surf. Hot mixing mattered. They used quicklime so reactive that it created lime clasts, bright, brittle nodules embedded through the mortar. To a modern eye, those clasts look like mistakes. They aren't. They're release capsules. When microcracks form and salty water seeps in, the clasts shatter, dissolve, and pump reactive calcium into the gaps. New calcium carbonate grows, cracks knit. The structure doesn't just resist the sea, it recruits the sea to repair itself. Meanwhile, at the interface where ash meets seawater, strange minerals precipitate, tobermorite and friends, crystalline reinforcements that thread the matrix. Picture it. Waves hammer, ions migrate, crystals bloom along weaknesses, and the pier hardens with age. That isn't romanticizing ruins. Core samples pulled from ancient breakwaters show exactly those phases, exactly that mechanism. The sea writes a maintenance plan into the concrete's microstructure. Human moments put skin on the chemistry. A foreman on a Roman quay judges the slake by heat on his palm. He orders ash from a particular cove because the color tells him the mix will set fast and hold. A crew tips the formwork into the tide, hears the hiss as seawater bites hot lime, and smiles. They don't say nanoparticulate architecture. They say, this pier will still be here when our grandsons fish from it. Impact spills forward in a straight line you can trace. Modern researchers study those clasts under microscopes, then make new mixes with deliberate hot lime inclusions. They crack the samples, add water, watch them heal, and file patents. Green concrete startups pitch self-healing binders that cut CO2 by extending service life. Civil engineers rework specifications for marine structures, drafting clauses that would have made a Roman builder nod. An ancient recipe becomes a modern climate strategy. So where's the suppression thread? It's messier than a villain. Recipes fragment. Guilds guard ratios as insurance. Emperors subsidize some sources of ash and neglect others. Later polities lose quarries, lose masons, lose the language of the craft. Medieval builders inherit the word pozzolana but not the full choreography, hot mixing, placement in active seawater, patience. The knowledge doesn't vanish behind a curtain, it thins until it tears. There were choices too. When imperial trade routes snapped, the supply chain for the right ash broke with them. You can't wish Tobermory into existence with the wrong volcanic chemistry. Substitutes worked inland, harbors failed at sea. In archives, formulas devolved into adjectives, best ash, strong lime, and then into silence. Secrecy, scarcity, and collapse produced the same outcome, forgetfulness. Let's draw hard lines between fact and myth. There's no evidence of magical additives or alien binders. The magic is process. Volcanic ash rich in reactive silica and alumina, quicklime hot mix to create clasts, placement in seawater to kick the chemistry. That combination scales from cisterns to amphitheaters to piers. It isn't trivial, it isn't accidental, and it has boundary conditions you can test. Meanwhile, the pattern we keep seeing returns. Craft encodes algorithms without writing them down. A mason's eye stands in for a lab instrument. A crew's rhythm becomes a Turing profile. When the line of masters breaks, the algorithm dies, even if the ruins remain. That's the practical meaning of suppression by neglect. No bonfires, just apprentices who never learn to feel for heat in the mix.